I'm happy to introduce our first keynote speaker of today. She's a consultant with Cradle to Cradle trainer with EPEA International, and she has trained hundreds of architects, designers, engineers, and resource managers, including at Venlo City Hall and the preschool in Ronneby, Sweden, which the BAMB team has recently visited. Katja Hansen is also lead partner for lead developer for the material passports, which will play a pivotal role in the BAMB projects and which will be discussed later today. But her keynote will be focusing on design. So please welcome Katja Hansen.
Thank you. As I was walking through the neighborhoods here yesterday, I was reminded of the urge and need towards circular building developments. It's a huge task, I was also reminded once again, but I don't think failure is an option. So how can we use BAMB to support great designs? Because it's designs that this is really all about, and making technology work. Material value in commodity markets for investors usually goes up. It's volatile, but it goes up. So if you invest in resources, you hope to make money. If you're developing a building and you own it, you actually lose money. You may change that perspective through accounting, because you write off the building, but you don't use up the materials. So you still have all the materials that you originally purchased in the building, yet after the use period is over, it becomes a liability. You have to pay for someone to carry it away. Is that a good business model? I think we all agree, that's why you're here. There is definitely a way to improve that. Materials. The built environment uses up about 40 to 50% of all the resources worldwide, the built environment. So a lot of materials are locked in our built environment. So how do we move from a demolition liability towards healthy material assets that have value? Let's see how we can actually affect that paradigm change. How can we move to positive impacts? Currently, a lot of our efforts are still focused on being less bad, minimizing our negative footprint. We recycle, yes, we've gotten quite good at it, but honestly, we're downcycling. If we turn a glass bottle, a yogurt container, into a flower pot, we can never again make a water bottle from it. So we deteriorate the quality of the material. And so it's still part of a linear economy paradigm because we're not maintaining the quality of the materials for as long as possible. That is one of the main focuses in a circular economy, maintaining quality of materials for as long as possible. We can also reduce, being very efficient in terms of material use, water use, energy use. But that is still only minimizing our negative footprint. If we're really walking towards effectiveness, as we heard in the introduction as well, so towards a positive footprint, we want to look at how can we maximize positive impacts. That we can do through upcycling, maintaining the quality of materials throughout many use cycles for as long as possible. Reusing not only materials, but components and systems for as long as possible. I think for the built environment, the value for building owners really is not in the base materials, but in the components and in the systems. And overall, to really move to circular design, we need to rethink. This is not going to happen incrementally. We need to rethink how to design products for circularity. It's not going to work by just thinking, what can we do with today's waste? And in the following slides, I'll show you how the design thinking is really the foundation towards circular economy and circular product design. The cradle-to-cradle cycles are really the basis for circular economy products. It might be very simple, but that's good because then most people can understand it. We look at our products in a way that we basically ask the question, do we consume the product? Does it dissolve in the process of being used? It happens with food, it happens with toilet paper, it happens with toothpaste. That product you cannot recover really after you've used it. So it's really consumed, which means it enters the biosphere through your body, through water, through air. It ends up in the biosphere. So there it should be a resource so you can recreate that resource. That is the part that we call the biosphere. It is much, much more than just the ecosystem around us. It's all the products that we design to be consumed. And we don't have enough time, but you can each now think of a product that you would classify as a consumption product. All other products that do not disintegrate during the use phase are actually only providing you with a service. And buildings are mostly such. So they're part of the technosphere. So inherently, they're designed for recoverability because they stay in one place and you can get at the resource for the next use. So that is the design parameter that you need to look at. I said earlier, the circular economy isn't just based on trying to turn our waste products into new products. That's still linear economy thinking. So when we think of designing products for the circular economy, it really starts with design, right here at the beginning. When we design a product, we not only design it for the functionality of the first use phase, we design it with the next and the next and the next phase in mind. So it poses a totally different design challenge for most of our products and systems. One of the next steps is the composition. I mentioned quality. We really need to maintain the quality of our products. Additives are a very important thing, for example, in plastics. We're talking about pure plastic fractions, polypropylene, polyethylene. Well, anyone with a little bit of chemistry background knows that any plastic polymer only has its functionality due to additives. That poses big, big challenges for the recycling, which is why most plastic today is being downcycled. So again, in the very beginning of designing, of conceiving, of formulating our products, we have to keep that circularity aspect in mind. What do we want to achieve in the next design phase? Component production, product assembly, and distribution are along the product chain. Product assembly, interestingly enough, is a very key point for products and systems because when we design products to be disassembled, we have found that the assembly also saves money, goes faster, is easier. So thinking in advance of the disassembly of the product also allows us to simplify and improve product assembly. And then you see service or consumption. So that's the pathway that our product enters. And ideally, you have a collection phase, clearly for service products, but also for some of the consumption products. The technosphere that you saw earlier then splits up into various cycles: maintenance, redistribution, refurbishment, disassembly, remanufacture, and component harvesting, disassembly, recycling, and upcycling. So this goes down in the level of product integrity. You try to do as much as you can with the product and system intact, but you may also break it down depending on what the next use scenario is. In all of those, the know-how feedback loop is very important, because as we try to improve our products, we learn. So it has to go back into the design, into the product formulation process. In the biosphere, of course, we're frequently facing the consumption, which is basically a dispersal of the bionutrients, which means that it really has to be suitable for the biosphere. But we can also collect some of these bionutrients and then reprocess them into new products that are designed to create new biological resources. So that is a complex diagram, but it is basically the foundation, the framework in which we can determine how do we design products for circularity. And because it's a big bite, I'll actually give you examples for each of these two cycles for products that have been designed for circularity. But before I do that, I want to stay at the building level, and just some examples of projects that we've worked on that use circular design approaches are, of course, the Ronneby Preschool, which some of you in the room have actually seen in person. The interesting thing to highlight, there's lots to say about it, and I don't have time this morning to go into detail for every project, but for Ronneby, one of the highlights, I think, was that they actually asked one of the most important stakeholders in the process, and that's the children who visit the preschool, how would they imagine a preschool that they would really like to go to? And they had a creative session with the kids, and the kids actually influenced the design of the preschool. I'm sure that was highlighted when you were in Ronneby. It's a really interesting story. Otherwise, talk to Martina, who's sitting here in the second row, and she can tell you all about it. Venlo City Hall, I don't know, I haven't seen if someone is here from Venlo. This is still a graphic, but the building actually is almost ready for use, so it looks like just exactly like that. And they've implemented a lot of features, both on the Biosphere and Technosphere side for their new City Hall. Many of you have heard of Park 2020 as one of the shining examples on a business park development with many buildings. This is the Fox Vacancy building, but there are several buildings on that side, on that business park, that are designed for circularity. And last but not least, a project that is very dear to me because I worked on it for over a decade in Brazil and in China, in the favelas, is bionutrient recycling. What you see here is actually a very low-tech wastewater treatment facility, except we call it a bionutrient recycling facility, because what we showed is that through the process of recovering the nutrients from the wastewater, we created clean water as a byproduct. So the main intention of the project was, of course, to eliminate the pathogens, but mostly to create valuable products. So these are farms. It was a previous project financed by the Commission, and there's actually quite a bit of documentation. Anyone who wants to know more about it, please speak to me after this talk. Now, how do we get to product circularity? Material passports were mentioned in the introduction. They're really the one-stop shop. So the place to go for product circularity because they allow us to define various aspects, and we'll go into more detail with Lars a little later. But what they really do is encourage circular product designs. They encourage to describe the material and component recovery systems, and they actually support chain of possession partnerships. You know that I deliberately chose the word chain of possession rather than supply chain, because the supply chain is still very much a linear economy approach, whereas in the circular economy, everyone owns the material at some point, but then they pass on that possession of the product or component, and with that, they pass on the intelligence, the information about that system and component. And that is really what material passports are also intended to facilitate. It comes back to quality. It clearly speaks to improving the quality, but also the value and the security of supply of materials, because we've seen lots of incidences in the last years where the pressure on materials in Asia has led to shortages in automobile production in Europe, and there's lots of other examples. So how long does Europe want to continue exporting their waste materials, which are resources, back to Asia, where they're inappropriately recycled because children take apart televisions and computers? Or can we actually design those products in a way that that doesn't happen? It also happens to big container ships, as you know, and what happens to our buildings? So, from demolition liability to a healthy material asset, there is a roadmap. We're not going to get there from today to tomorrow, but we have to set the goal, the ambition to actually create healthy material assets. And again, when you step outside and you look around, the question is, aside from this building that has implemented first thoughts, where do we see that in the built environment? Nitesh is going to talk about some other positive examples, but the challenge is to scale those up. So knowing what is in our buildings, trying to assess that, design them for quality, facilitating circular economy material use, include clearly designs for extraction and disassembly, reversibility, a very important point, and system partnerships. A company, whether it be a building developer or a product developer, cannot move towards the circular economy alone. I earlier said it's chain of possession partnerships, it's system partnerships. So that's why launching the network today, I think, is such a crucial step in our efforts with BAMB. So the material passports connect each of those steps. I want to give you an example now, as I promised, for the two cycles. The example of light as a service. There's a small company called BB Light Concepts that develop light pipes. And they have some outstanding key features. The capital expenditures are through light leasing concept or take concept reduced for the building owner. So you save basic investment costs. You improve the value because the system is set up for flex use and material use. You save through quicker assembly installation, which also relates to the flexibility because a lot of buildings are constantly repurposed. And you basically have improved functionality and quality through the glare-free lighting that the light provides. And you also have operational expenditure savings because you can manage the energy use. All of that is quite well documented. So coming back to this complex graphic, how does that actually apply? Redesign and prototyping, they really looked at the light pipe in a way asking how can we design it for the circular economy. They looked at the materials and excluded, for example, critical materials. They designed the components in the light system in a way that they could be easily recycled, including glues, which they tried to avoid. The component productions, again, go towards production of the light. How does it actually reduce the number of different plastic parts, for example? So you have a monomaterial approach. Product assembly, how can we have reversible connectors rather than gluing things and making different materials difficult to take apart? They clearly provide the light as a service, which includes the maintenance. The whole thing is designed for disassembly, remanufacture, and component harvesting. And they went through several feedback loops to actually improve the light. So each of these items to be covered has an added value and is a value proposition that is also part of the passport. There are other systems, for example, that improve air quality. The KE FiberTech Cradle vent, which are the blue pipes that you see in the picture, are textile air ducts, which have many, many features that are positive for the indoor air quality, which, as you know, in most buildings is worse than the outdoor air in Brussels, London, or Berlin. So indoor air quality being a big issue in the built environment, how can products support positive indoor air quality? The Deso Airmaster is another example. It's a carpet that actually absorbs fine dust in the air and cleans indoor air. So these are all products and systems that contribute to positive indoor air quality. Now moving from the technosphere to the biosphere, fertilizer extracted from wastewater. Crystal green is one example. It's a magnesium ammonium phosphate, which is a slow release, so it's a good fertilizer that doesn't immediately get into the groundwater. And interestingly enough, it also reduces energy costs in wastewater treatment, because the earlier you remove the phosphate, you lower the BOD or the COD of the wastewater and thus have to put less energy into treating the wastewater. So it's a very beneficial thing. And going back to the graphic again, they looked at a slow-release fertilizer and what they could actually create. They used magnesium rather than iron, which makes it more bioavailable. The product assembly is actually that of a chemical precipitation in the wastewater treatment. So the product is both consumed and provides the services to the wastewater treatment facility to then become a fertilizer product, which is clearly consumed because it's dispersed on the golf course or on your field to create new biological resources, which then return to create new biological resources. So for the biosphere, it's much, much easier to foresee continuous loops. And that's something I want to highlight. We talk about closed loops a lot. It puts a total block for most manufacturers because they think if I have to close my loop, it means I have to take back my washing machine. It means I have to take back my air filtration system. That's not really what we need to focus on in a circular economy. We need to define materials and components in a way that the next user can also make use of it. And we have continuous material loops rather than closed loops. It opens huge opportunities in that area. A green fence. Well, obviously that's not a green fence. University of Wageningen has shown different fence systems that have added value, whether you look at a water-based system or a bee hotel or a berm that has a diverse ecosystem or a green land-based ecosystem. Those are all fences, so they have the functionality of a fence, but they have added value. They have positive impacts. So buildings made of products designed for reversibility are valuable material banks. Thank you very much.